All right, guys, here's a little help for number 15 on the homework. So I'm going to run through some steps with you. So here's 15. It has some things we started talking about today in class, but weren't able to finish. But I highlighted a few. See that 6 in the denominator? It's got to be a 1. We've got a minus in between there. That really is a big driver, having a 1 there, because what we want to have is an ability to identify the r and an initial value. So there's the minus that I was telling you about. Now, this is the way we're going to get at that first. You want to get that 1 in the denominator. So I'm going to multiply top and bottom by 1/6, and that allows us to have x over 6, and then the denominator is 1 minus 7/6x, 7/6 x, and that's an r in the parentheses, and our initial value is x over 6. I like to check those, like I told you guys in class, an initial value with a little quick long division just to make sure that's the right initial value. If you're trying to get 6, how many times does 6 go into x? It does go in 1/6 x times, or x over 6. So we know we're off to a good start. I'm going to finish from there using the formula because it's in geometric form. So what I can do is I can take that initial value, x over 6, and I can simply start my expression with that and then take the r to the nth power. Now that's for n equals 0. So that's to start at n equals 0, and that's how we've been kind of framing everything so far. Well, the problems in the book want n equals 1. You just got to do a quick shift. You got to add 1 to the counter. Instead of n equals 0, make n equals 1. And the way you adjust it in your series is you simply counter it with taking away 1 from all the n's within the expression itself. So you can see that quick calculation there. That's our series for this, x over 6. 7x over 6 to the n minus 1. I've tried a couple different similar forms, and it took these. The only issue is when I or anybody else I chatted with, we forgot that it was n equals 1 in the series instead of n equals 0, and we forgot to offset those powers. So there's multiple parts to these. Usually what we end up with is getting an interval of convergence or radius of convergence, center, etc. So those are all related. If you want to do that, of course, we're talking about using the ratio test. The rare case that it's all to the nth power, we can use the root test. But this one takes a little bit of definite ratio test. All the n's become n plus 1s. We're going to divide it then by the original. But to do that, I'm going to clean this thing up. So check out what I'm doing. I'm going to separate the 7s, 6s, and x's out. So they're all on their own, because ultimately that's the stuff that cancels in the ratio test. So I isolated 7, 6, and x in their respective powers. Then from there you can do the n plus 1 version times the reciprocal of the original, and then watch the cancellation unfold. So those are the cancellations. I did them a little quickly there. Ninja canceling, I like to call it. And what ultimately emerges is that 7x over 6 is less than 1. Now, it might be difficult to see the radius in there, but if you isolate x to x minus some value, then that isolates your center and radius. So in this case, it's pretty easy to see this is between negative 6/7 and 6/7, and the center would be 0, making the radius 6/7. A quick way to do that also is just multiply out that 6/7, or multiply out by 6/7 to get x alone, and then say, oh, there's nothing subtracted from x, so it's center of 0, and then your radius is 6/7. The interval subsequently is between negative 6/7 and positive 6/7. Plugging that back in to test the interval, you can kind of see back here in the original, if I put in that 6/7, we are going to end up with a 1 inside there to a power, and we know that's going to diverge. So that's a quick test, but I don't know if it asks for the interval or not. You guys can kind of make that call. Hope that helps.